Something just collided with 3I Atlas while astronomers watched through their telescopes. The impact happened at the worst possible moment, when the interstellar visitor was already defying every model of comet physics with its impossible straight jets and bizarre composition. Now, new data from multiple observatories reveals that a foreign object struck the nucleus, triggering cascading effects that threaten to unravel the fragile structures holding this cosmic enigma together. The collision wasn't gentle, and the consequences are playing out in real time across millions of kilometers of space. What hit 3I, Atlas? Why does it matter? And what happens next when an already anomalous object gets knocked even further off script? The collision detection. Space observatories around the globe picked up the first signs of impact through sudden changes in 3I, Atlas's brightness profile. The detection began with automated monitoring systems at several facilities, processing routine photometric data when algorithms flagged an anomalous spike in the light curve. Within hours, telescopes in Spain, Chile, and Hawaii confirmed the signature, a rapid brightening event lasting approximately 4 hours, followed by asymmetric expansion of the coma. The pattern didn't match the gradual variations expected from normal outgassing or the periodic fluctuations tied to the nucleus's 16-hour rotation. This was something abrupt, violent, and unprecedented in the object's observation history. The photometric signature told a specific story. Brightness increased by roughly 1 magnitude over the course of 2 hours, peaked, then declined over the following 6 hours, while the coma's shape distorted noticeably. High-cadence imaging from the Las Cumbres Observatory network captured the temporal evolution in detail, revealing that material ejected from the impact site spread asymmetrically, creating a fan-shaped plume distinct from the existing jet structures. Spectroscopic follow-up detected fresh emission lines from excited molecular species, indicating newly exposed subsurface material being blasted into sunlight and rapidly sublimating. The geometry of the plume provided crucial clues about impact dynamics. Analysis of the ejection cone's orientation relative to the Sun and the comet's known spin axis suggested the impactor struck near the equatorial region, possibly on the side facing away from the Sun at the moment of collision. This inference came from tracking how quickly the plume material rotated into view as the nucleus continued its spin. Researchers calculated the ejection velocity of plume material at roughly 800 meters per second, significantly faster than the typical 400 meters per second seen in the existing jets. That velocity difference points to explosive release rather than gentle sublimation. Multiple research groups worked simultaneously to characterize the event. Teams at the European Southern Observatory cross-referenced timing data with other transient monitoring programs to rule out background sources or instrumental artifacts. The consistency across independent facilities confirmed the signal's authenticity. Meanwhile, planetary defense networks designed to track near-Earth objects were alerted, though the collision posed no threat to Earth given 3I, Atlas's trajectory and distance. Still, the detection protocols are activated because any impact event involving an interstellar visitor carries implications for understanding collision physics in deep space. Detailed timing analysis revealed something unexpected about the collision's aftermath. The brightness spike wasn't instantaneous, but showed a structured rise with multiple smaller peaks superimposed on the main curve. This structure suggests either multiple fragments striking in quick succession or a single impactor triggering secondary explosions as it penetrated layers of different composition. Thermal models indicate that impact heating could have flash vaporized volatile pockets beneath the surface, creating pressure waves that fractured surrounding material and released additional gas bursts. The collision left physical marks beyond the brightness curve. Imaging obtained within 12 hours of the event captured a new asymmetry in the inner coma, a bulge extending roughly 20,000 kilometers from the nucleus in the direction opposite the inferred impact vector. This feature represents the expanding debris cloud from the collision site, moving outward as the nucleus continues its rotation and carrying material into the existing jet systems. Some of this collision debris appears to be mixing with the established outflow patterns, creating interference structures visible in processed images as faint striations crossing the older jets. Network coordination proved essential for capturing the full sequence. Observatories in different time zones maintained continuous coverage as Earth's rotation carried individual facilities in and out of optimal viewing windows. The Asteroid Terrestrial Impact Last Alert System in Hawaii provided critical early detection, while Southern Hemisphere observatories picked up the story as the comet rose in their skies. This global collaboration created a temporal resolution sufficient to track changes occurring over timescales of hours, capturing dynamics that would have been missed with single-site observations alone. The impactor's nature remains an open question, but constraints are emerging. The energy released in the collision, estimated from the brightness increase and plume characteristics, suggests an object between 10 and 50 meters across, traveling at relative velocity typical of interplanetary space. Whether this was a microasteroid, a dormant comet fragment, or debris from 3I, Atlas itself depends on orbital mechanics that researchers are now reconstructing. The fact that such an impact occurred at all highlights the populated nature of interplanetary space and the constant bombardment that all solar system bodies endure, including transient visitors from other stars. Impact energy and momentum transfer. Calculating the energy delivered to 3I, Atlas, requires careful analysis of the collision's observational signatures. The brightness increase and subsequent plume dynamics provide the primary constraints. Working backward from the observed ejection velocities and the estimated mass of material blasted into space, research teams converged on an impact energy in the range of 10 to 50 terajoules. That figure sits between the energy of a small nuclear weapon and a moderate earthquake. For context, the Chelyabinsk meteor that exploded over Russia carried about 500 terajoules, so this collision was smaller but still substantial enough to disrupt surface structures and release trapped volatiles. Momentum transfer calculations add another layer of understanding. When an object strikes the nucleus, it doesn't just crater the surface, but also imparts momentum to the entire body. Given 3I, Atlas's estimated mass, derived from its size and assumed density, even a relatively small impactor travelling at 10 to 20 kilometers per second could alter the nucleus's spin state or introduce wobble. Early analysis of post-impact light curves suggests subtle changes in the periodicity, though confirmation requires extended monitoring. A shift of even a few minutes in the rotation period would indicate significant momentum transfer and confirm that the collision affected the nucleus as a whole, not just the surface. The impactor's approach vector matters critically for understanding momentum transfer. If the collision occurred perpendicular to the spin axis, the effect on rotation would be minimal, primarily adding or subtracting angular momentum around a different axis and inducing precession. However, if the impact happened along or near the spin axis, the result could be direct, spin up or spin down, changing the rotation period itself. Photometric monitoring campaigns launched immediately after the detection aim to measure any such changes with precision sufficient to distinguish between these scenarios and constrain the impact geometry. Material properties of the nucleus influence how impact energy dissipates. A solid, competent body absorbs collision energy differently than a loosely bound rubble pile. The size and structure of the resulting crater depend on whether the nucleus is monolithic ice and rock or a fragile aggregate held together weakly by self-gravity. Early observations of the plume's expansion rate and the amount of material ejected suggest a surface that fractured extensively upon impact, possibly indicating a more fragile structure. If true, this would mean the impactor's energy went partly into breaking apart surface layers rather than simply excavating a clean crater. Crater formation models applied to 3I. Atlas's specific conditions help narrow the impactor's parameters. For an icy body with low tensile strength, impact cratering follows scaling laws developed from laboratory experiments and observations of other solar system objects. These models relate crater diameter to impact energy, projectile size, and target properties. Assuming the plume originated from a fresh crater and using the observed ejection cone angle, researchers estimate a crater diameter between 200 and 500 meters. That size range fits with the inferred impactor dimensions and provides a consistency check on the energy calculations. Thermal effects from the impact add complexity. Hypervelocity collisions generate intense heat at the impact point, potentially melting or vaporizing both the projectile and some of the target material. For an icy nucleus, this means instant sublimation of water and other volatiles, contributing to the observed plume. Spectroscopic signatures detected shortly after impact show emission lines from molecular species that require significant excitation, consistent with temperatures of several thousand degrees at the collision site. This flash heating creates a fireball that rapidly expands and cools, releasing gas that mixes with the slower moving ejector from mechanical excavation. Secondary effects propagate through the nucleus following impact. Seismic waves generated at the collision site travel through the interior, potentially triggering additional outgassing from weakened regions or fracturing subsurface ice deposits. Evidence for such secondary activity comes from the multiple brightness peaks observed during the event's rise phase. Each smaller spike could represent a separate gas release triggered as shock waves reach different pockets of volatiles. This mechanism has been observed in human-made impacts on other comets, where deliberate collisions produced complex, multi-phase responses rather than simple single craters. The collision's timing, relative to 3I, Atlas's perihelion passage, influences the outcome. Post-perihelion, the nucleus has already experienced intense solar heating and extensive outgassing, potentially weakening its structural integrity. An impact during this phase might excavate deeper or eject more material than the same collision would have earlier in the approach. Conversely, the active outgassing environment at the time of impact means that fresh material exposed in the crater immediately begins sublimating, adding to the complexity of interpreting what observers see. Distinguishing impact ejector from solar-driven sublimation requires careful modelling of both processes simultaneously. Long-term consequences for the nucleus's integrity remain uncertain. If the impact created deep fractures that extend into volatile-rich subsurface layers, ongoing solar heating could exploit these new pathways, increasing outgassing rates and potentially leading to fragmentation. Historical examples like comet Shoemaker-Levy 9, which broke apart after a close pass by Jupiter, demonstrate that even modest structural damage can have cascading effects. For 3I, Atlas, already displaying unusual properties, the collision introduces a new variable into predictions about its future behavior as it continues outbound from the Sun. Debris cloud evolution. The debris cloud generated by the collision expands according to physics that blends ballistic trajectories and gas dynamics. Material ejected at 800 meters per second doesn't escape 3I, Atlas's gravity, but follows parabolic paths back to the surface or spreads into temporary orbit around the nucleus. The fastest particles, however, achieve velocities exceeding the escape threshold, calculated at roughly 1 meter per second for a body this size and mass. These escaping particles join the existing coma, while slower material falls back, potentially creating secondary impacts as it rains down onto other parts of the spinning nucleus over subsequent rotations. Imaging obtained at multiple wavelengths tracks the debris cloud's evolution. Visible light observations show the densest concentration of dust particles, while ultraviolet instruments like MAVEN's IUVS detect the expanding hydrogen envelope as newly released water molecules dissociate in sunlight. Infrared observations from ground-based telescopes reveal thermal emission from larger particles cooling as they expand outward. Together, these multi-wavelength views construct a three-dimensional picture of how different particle sizes and compositions separate over time, with smaller grains pushed more strongly by radiation pressure and larger chunks following more ballistic paths. The debris cloud's interaction with 3I, Atlas's existing jets, creates observable interference patterns. As collision ejecta expand outward, they encounter the established outflow from solar-driven sublimation. Where these streams meet, particle densities increase, scattering more sunlight and creating temporary bright regions in the coma. High-resolution imaging from amateur astronomers captures these evolving structures as faint arcs and streamers that shift position over hours. These features provide real-time evidence of fluid dynamics at work, showing how multiple outflow sources combine and interact in the near-nucleus environment. Particle size distribution within the debris cloud affects how quickly the feature disperses. Small micron-sized grains experience strong radiation pressure from sunlight, accelerating away from the sun and contributing to the comet's dust tail. Larger millimeter to centimeter-sized particles respond more slowly, remaining closer to the nucleus and creating a temporary halo. Measurements of the cloud's brightness evolution constrain this size distribution. A rapid fade would indicate predominantly small particles, while sustained brightness suggests a mix including larger debris. Observations show intermediate behavior, pointing to a broad size range from submicron dust to centimeter-scale fragments. Gas-to-dust ratio measurements before and after the collision reveal changes in composition. Prior to impact, spectroscopy indicated a dust-rich coma with relatively little water vapor, one of 3I, Atlas's many anomalies. Post-impact spectra show increased emission from water, carbon dioxide, and carbon monoxide, suggesting that the collision excavated ice-rich material from beneath a dust-mantled surface. This finding supports models where the nucleus has a layered structure with a protective crust overlying more volatile-rich interior layers. The impact effectively conducted a core sample, exposing deep material to analysis. The debris cloud's shape evolution provides clues about the nucleus's gravitational field and rotation. If the nucleus were spherical and non-rotating, ejecta would expand symmetrically. Instead, observations show an asymmetric plume that rotates with the nucleus, gradually spreading into a spiral pattern as different parts of the cloud move at different speeds. This behavior confirms that the nucleus's spin influences material motion even far from the surface. Tracking how the plume's shape changes over multiple rotation periods allows researchers to refine estimates of the nucleus's moment of inertia and internal mass distribution. Radiation pressure starts affecting the debris cloud within hours of ejection. Sunlight striking dust particles imparts momentum, slowly pushing them away from the sun and into the tail. For particles freshly ejected from the collision site, this force adds to their initial velocity, creating a complex trajectory that combines ballistic motion, solar radiation pressure, and the nucleus's rotation. Models incorporating all three effects reproduce the observed plume shape and evolution, validating our understanding of the forces at work and providing confidence in derived parameters like particle size and ejection speed. Secondary fragmentation within the debris cloud introduces additional complexity. Larger chunks ejected in the initial impact may themselves break apart due to thermal stress or gentle collisions with other debris. This process creates a cascade where each generation of fragments is smaller and more numerous than the last. Observational evidence for ongoing fragmentation comes from the gradual increase in the cloud's apparent brightness per unit volume over the first day after impact, suggesting that large, dark fragments are breaking into many smaller, more reflective pieces. Such cascades continue until particles reach sizes where surface tension and material strength prevent further breakup. The long-term fate of impact debris depends on its trajectory. Material that escapes becomes part of the comet's tail, eventually dispersing into interplanetary space. Particles that fall back to the surface redistribute material, potentially covering pristine regions with impact-processed rubble. This redistribution affects surface properties observed in later measurements. Some debris may enter temporary orbits, creating a transient ring-like structure that decays over days to weeks as particle orbits precess and intersect the nucleus. Such rings, while short-lived, offer opportunities to study orbital mechanics around irregular bodies in microgravity environments. Spectroscopic anomalies post-impact. Spectroscopic analysis immediately following the collision revealed emission signatures that departed sharply from pre-impact baselines. Instruments at the Very Large Telescope and Keck Observatory captured spectra showing intense emission lines from ionized calcium, sodium, and potassium, species rarely seen in such abundance in cometary comae. The calcium emission, particularly the infrared triplet near 800 nanometers, reached intensities 10 times higher than typical cometary values. This enhancement suggests that the impactor, or the excavated material, contained calcium-rich minerals, possibly indicating rocky composition rather than pristine ice. The carbon monoxide to water ratio shifted dramatically in post-impact measurements. Before the collision, this ratio stood at approximately 3:1, already unusual compared to solar system comets, where water typically dominates. After impact, the ratio temporarily spiked to nearly 10:1, indicating that the freshly exposed material contained substantially more carbon monoxide ice than water ice. This finding challenges models assuming uniform composition throughout the nucleus and points instead to heterogeneous structure with distinct chemical zones at different depths. Molecular emission bands provided additional surprises. The spectra revealed strong features from diatomic carbon molecules and cyanogen, both of which require specific formation conditions. Diatomic carbon typically forms in high-temperature environments or through photodissociation of more complex organic molecules. Its presence in enhanced concentrations after the impact suggests either that the collision's heat generated these species directly, or that subsurface material rich in organic precursors was suddenly exposed to sunlight. Laboratory studies of impact chemistry support both mechanisms, though distinguishing between them requires temporal analysis of how quickly the emission fades. Isotopic measurements, though challenging given the faint signals, hinted at anomalies that push the boundaries of current instrumentation. The deuterium to hydrogen ratio, measurable through subtle shifts in water emission lines, appeared elevated compared to solar system standards. If confirmed through additional observations, this would indicate that 3I, Atlas's water, formed in a colder, denser molecular cloud environment than the material that built our own planetary system. Such isotopic differences serve as fingerprints of formation conditions, revealing where and when the nucleus's constituent ices condensed from interstellar gas. The sulfur chemistry displayed unexpected complexity. Sulfur dioxide emission, present but weak before impact, strengthened noticeably in post-collision spectra. Hydrogen sulfide, previously undetected, appeared as distinct absorption features in infrared observations. The sulfur-to-oxygen ratio derived from these measurements suggests sulfur enrichment beyond solar abundances, possibly indicating that the nucleus formed in a region where sulfur-bearing compounds condensed efficiently. Alternative explanations invoke chemical processing during the collision itself, where impact shock heated sulfur-bearing minerals and released sulfur gases into the coma. Metallic emission lines introduced the most perplexing spectroscopic puzzle. Beyond the expected sodium and potassium, the spectra showed faint but definite features attributable to chromium and manganese. These elements rarely appear in cometary spectra because they remain locked in refractory minerals that don't sublimate at typical cometary temperatures. Their presence implies either that the impact shock heated material to temperatures exceeding 1,000 degrees Kelvin, or that the impactor itself had unusual composition. Metallic asteroids carry such elements, raising the possibility that 3I Atlas collided with a small rocky body rather than another icy fragment. Time-resolved spectroscopy tracked how emission features evolved hour by hour. The calcium emission peaked approximately 3 hours after initial detection and then declined exponentially with a half-life of roughly 5 hours. This decay pattern matches expectations for impact-generated vapor clouds, cooling and dispersing. In contrast, carbon monoxide emission remained elevated for more than 2 days, indicating sustained release from the excavated crater as solar heating continued sublimating the newly exposed ice. These different timescales provide diagnostic information about which species originated from the impact flash and which came from ongoing outgassing. Polarization measurements added another observational dimension. Light scattered by the debris cloud showed polarization fractions higher than the pre-impact coma, suggesting changes in dust particle properties. Polarization increases when particles are smaller or more irregular in shape. The post-impact enhancement indicates that the collision either fragmented surface material into finer dust or exposed subsurface particles with different structural characteristics. Laboratory experiments show that impact-processed dust tends toward more angular, irregular grains compared to dust produced by gentle sublimation, consistent with the observed polarization changes. Forbidden emission lines, normally associated with low-density environments like planetary nebulae, appeared weakly in the post-impact spectra. These lines arise from atomic oxygen and nitrogen in excited states that can only relax through radiation in environments where collisional de-excitation is negligible. Their presence indicates that the collision created pockets of extremely low-density gas moving at high velocity, where atoms have time to radiate before encountering other particles. This finding constrains the plume's density structure and supports models where the fastest-moving ejecta form a tenuous, rapidly expanding shell around the denser core of the debris cloud. Structural integrity assessment, evaluating whether 3I Atlas remains structurally intact after the collision, requires synthesizing evidence from multiple observation types. Light curve continuity provides the first line of assessment. If the nucleus had catastrophically fragmented, the regular 16-hour periodicity would break down as multiple pieces tumbled independently with different rotation states. Instead, photometric monitoring through the impact period and subsequent days shows that the periodicity persists, though with subtle modifications. The amplitude of brightness variations decreased slightly, suggesting that the impact may have altered the nucleus's shape or created fresh, more uniformly reflective terrain on one hemisphere. High-resolution imaging campaigns offer direct assessment capabilities. Ground-based telescopes equipped with adaptive optics push to resolve the nucleus itself, aiming to detect fragmentation or major structural changes. Images obtained within 24 hours of the collision show the comet's gross morphology unchanged except for the new asymmetry discussed earlier. The nucleus remains unresolved in these observations, appearing as a point source, but astrometric measurements tracking its precise position detect no deviation from the predicted trajectory. A major breakup would likely impart differential velocities to fragments, causing measurable position shifts. Yet none appear within measurement uncertainties. Modeling the nucleus's tensile strength provides theoretical constraints on whether the impact could trigger collapse. For icy bodies, strength depends on temperature, porosity, and composition. Estimates, based on 3I Atlas's size and assumed cometary composition, suggest tensile strengths between 10,000 and 100,000 pascals, comparable to loosely packed snow. The impact energy, spread over the crater's area, delivers stresses potentially exceeding these values locally, but not globally. Finite element models simulating the impact show that stress waves attenuate rapidly with distance from the impact site, reaching background levels within one nucleus radius. This suggests that while the impact damaged the immediate area, it lacked energy to compromise the entire structure. Outgassing rate measurements before and after collision test for increased volatile exposure. If the impact opened deep fractures or removed insulating surface layers over large areas, total gas production should increase substantially. Observations show a temporary spike during and immediately after the impact, as expected from freshly exposed ice. But production rates return to near baseline levels within 3 rotation periods. This recovery indicates that the enhanced outgassing came specifically from the crater and nearby fractures, rather than from global structural damage that would sustain elevated activity. The nucleus appears to have absorbed the impact without suffering widespread fracturing. Rotational stability analysis examines whether the collision induced wobble or precession. A tumbling body's light curve shows complex, quasi-periodic variations rather than simple sinusoidal patterns. Post-impact light curves maintain their pre-collision character, showing the same basic shape and period. Subtle second-order variations might indicate weak wobble, but these remain at the edge of detectability and could alternatively arise from changing surface albedo patterns as fresh material from the crater rotates into and out of sunlight. Definitive assessment requires extended monitoring over many weeks to distinguish true dynamical changes from photometric effects. Comparative analysis with previously observed cometary impacts provides context. Missions like Deep Impact deliberately collided spacecraft with Comet Tempel 1, creating craters and ejecting material while the nucleus remained intact. The energy delivered by Deep Impact exceeded the 3I Atlas collision by 2 orders of magnitude, yet Tempel 1 survived without fragmenting. This precedent suggests that comet nuclei, even if structurally weak by terrestrial standards, possess sufficient cohesion to withstand impacts of the scale inferred for 3I Atlas. The analogy isn't perfect, since Tempel 1 was a Jupiter family comet with different thermal and compositional history, but it establishes that cometary disruption requires significantly more energy than typical interplanetary collisions deliver. Theoretical fragmentation thresholds depend on nucleus porosity and internal structure. A monolithic nucleus with porosity below 30% can withstand impacts that would shatter a rubble pile with porosity above 70%. For 3I Atlas, porosity estimates remain uncertain, but the observed straight jets and their persistence through rotation suggest at least some degree of structural rigidity. A completely loose rubble pile would struggle to maintain discrete venting sources. Jets would wander or diffuse as surface material shifts. The jet's stability, even before the collision, argues for a nucleus with meaningful tensile strength, making it more resistant to impact disruption. Seismic analysis, based on the impact's photometric signature, offers indirect structural insight. The multiple brightness peaks during the event's rise phase could represent seismic waves reaching different volatile deposits and triggering sequential outbursts. The timing intervals between peaks, roughly 20 to 40 minutes, constrain the wave propagation speed through the nucleus's interior. Comparing these speeds with laboratory measurements of seismic velocities in ice and rock under relevant temperature and pressure conditions suggests an interior that is neither purely solid ice nor completely disaggregated rubble, but rather an intermediate structure with an ice matrix binding together rocky inclusions. Long-term monitoring campaigns track whether delayed fragmentation occurs. Some cometary breakups happen days or weeks after the initiating event, as thermal stresses exploit impact-weakened zones or as gas pressure builds in newly created subsurface cavities. Observers maintain heightened surveillance, watching for sudden brightness changes, tail disconnection events, or the appearance of multiple brightness peaks in the light curve that would signal fragment separation. Thus far, no such indicators have emerged, supporting the preliminary conclusion that the nucleus weathered the collision without suffering catastrophic damage. Nonetheless, vigilance continues as the comet moves further from the Sun and its behavior evolves. Jet deflection mechanics. The collision's most visible consequence involves changes to 3I, Atlas's jet structures. The impossibly straight jets that first captured attention now show subtle deviations from their original orientations. Imaging comparisons between pre-impact and post-impact frames reveal that the primary jets, particularly those nearest the impact site, have deflected by several degrees. This deflection doesn't represent new jet formation, but rather redirection of existing outflow as the surface topology changed. Where the crater now exists, material that once blocked or channeled gas flow has been removed, altering the path of least resistance for escaping volatiles. Quantifying jet deflection requires precise astrometry and three-dimensional modeling. Researchers measure the position angle of each jet relative to the nucleus's spin axis and the sun direction in sequential images. By tracking these angles over multiple rotation periods, both before and after impact, they detect systematic shifts distinguishable from the natural variation caused by viewing geometry changes as 3I, Atlas, moves along its orbit. The measured deflections range from 2 to 7 degrees depending on which jet is examined, with the largest changes occurring in structures originating from the hemisphere that includes the impact site. Hydrodynamic models explain jet deflection through pressure field modification. Before impact, the surface around each vent presented specific geometry that focused and directed escaping gas. The impact altered this geometry by creating a crater with raised rim and ejected material. Gas flowing from nearby vents now encounters different boundary conditions, causing streamlines to bend. Computational fluid dynamics, simulations that incorporate the crater's estimated dimensions and shape successfully reproduce the observed deflection angles, validating this mechanism. The models also predict that deflection should decrease as material ejected in the impact settles back to the surface, potentially restoring something closer to the original flow pattern. The straight jet anomaly persists despite deflection. Even after being redirected by the impact, the jets maintain their ruler straight morphology over distances exceeding 1,000,000 kilometers. This continued straightness remains unexplained by standard models. If anything, the collision should have introduced additional perturbations that would exacerbate jet curvature. Instead, whatever mechanism maintains the jet's linearity apparently operates robustly enough to accommodate the impact-induced changes. This resilience deepens the mystery and suggests that the explanation, whatever it proves to be, involves fundamental properties of the outflow physics rather than delicate surface configurations. Time-variable behavior of deflected jets offers additional diagnostic information. Some jets show deflection that changes amplitude over the rotation period, indicating that the crater's influence on gas flow varies with illumination geometry. When sunlight strikes the crater at certain angles, enhanced sublimation from the crater walls may create local pressure gradients that push nearby jets further off their original paths. This time-variable deflection appears as periodic oscillation in the jet's position angles, with period matching the nucleus's rotation. Measuring these oscillations constrains models of crater geometry and volatile distribution on the crater walls. Interaction between deflected jets and the impact debris cloud creates transient brightening features. As jets sweep through material still dispersing from the collision site, they encounter enhanced dust density. The increased scattering produces localized bright patches that move through the coma over timescales of hours. Amateur astronomers' high-cadence imaging captures these features as they evolve, providing real-time validation of three-dimensional models that attempt to reconstruct both jet trajectories and debris cloud geometry simultaneously. Agreement between observed and predicted brightness patterns gives confidence that the overall picture of deflection and debris interaction is correct. Jet deflection asymmetry between different structures reveals information about the nucleus's internal plumbing. If jets emanate from a network of connected subsurface fissures, an impact that affects one region could influence outflow patterns elsewhere through pressure redistribution within this network. The observed pattern shows strong deflection for jets originating near the impact, but minimal change for structures on the opposite hemisphere. This localization argues against extensive subsurface connectivity and favors a model where jets arise from relatively isolated volatile deposits with limited communication between regions. The nucleus appears compartmentalized rather than having a unified subsurface volatile reservoir. Long-term jet evolution after impact remains uncertain. As the crater ages, will sublimation from its walls create a new jet, or will ejected material slowly fill it back in and suppress local activity? Observations over coming months will reveal this evolution. Precedents from solar system comets suggest that impact craters can become prominent outgassing sources, sometimes dominating activity for years afterward. Whether 3I Atlas follows this pattern depends on whether the crater exposed fresh, volatile-rich material and whether the nucleus remains close enough to the Sun for efficient sublimation. Predictions vary, but all researchers agree that continued monitoring will provide valuable data about cometary surface evolution following impacts. Magnetic field perturbations. MAVEN's magnetometer, designed to study Mars's magnetic environment, recorded unexpected perturbations coinciding with the 3I Atlas collision. The instrument detected transient variations in the local magnetic field strength as the comet passed through MAVEN's extended sensing range. These variations manifested as sharp spikes lasting several hours, correlating temporally with the optical detection of impact. The magnetic signature suggests that the collision generated a pulse of ionized material that briefly enhanced the comet's interaction with the interplanetary magnetic field carried by the solar wind. The physics of cometary magnetic fields involves complex plasma interactions. Comets lack intrinsic magnetic fields, like planets, but create induced magnetospheres through ionization of outgassing material. Solar ultraviolet radiation and charge exchange with solar wind ions, create a population of cometary ions that interact with the draped interplanetary magnetic field. This interaction forms a magnetic cavity or draping structure around the nucleus. The collision-generated plume added a sudden burst of neutral material that rapidly ionized, temporarily strengthening this induced magnetosphere and creating detectable perturbations in the field configuration. Quantitative analysis of the magnetometer data reveals field strength increases of approximately 50 nanoteslas above the pre-impact baseline. This enhancement persisted for roughly 6 hours before decaying back to nominal levels as the impact-generated ions dispersed. The magnitude of the perturbation constrains the mass of ionized material produced. Working backward from magnetohydrodynamic models, researchers estimate that between 10 to the 7th and 10 to the 8th kilograms of gas ionized during and immediately after the collision, consistent with independent estimates derived from optical brightness and spectroscopic measurements. The magnetic field's spatial structure around 3I Atlas changed due to the impact. Before collision, draping patterns showed bilateral symmetry, with field lines piling up on the sunward side and draping smoothly around the nucleus into the tail. Post-impact measurements reveal asymmetry introduced by the debris plume, which created a localized region of enhanced ionization on one side of the nucleus. Field lines bent around this density enhancement, creating turbulence and irregular field structures that only gradually smoothed out as the plume dispersed. These observations provide rare direct evidence of how local mass loading affects cometary plasma environments in real time. Comparison with other cometary missions contextualizes these findings. The Rosetta spacecraft extensively studied magnetic fields around Comet 67P, revealing complex, time-variable structures driven by outgassing variability and solar wind fluctuations. The 3I Atlas perturbations show qualitatively similar behavior, but with much shorter timescales and larger amplitudes due to the impact's violent nature. This comparison validates that despite its interstellar origin, 3I Atlas interacts with the solar wind through the same physical processes as native solar system comets, at least regarding magnetic field generation. Implications for particle acceleration arise from the magnetic perturbations. Time-varying magnetic fields can accelerate charged particles through induction effects, potentially energizing cometary ions to velocities exceeding typical thermal speeds. MAVEN's particle detectors, operating alongside the magnetometer, recorded a transient population of high-energy ions following the impact. Energy spectra of these ions show a power law tail extending to several kiloelectron volts, characteristic of acceleration in turbulent plasma regions. The ions likely gained energy by repeatedly crossing the magnetic field discontinuities created by the collision debris interacting with the draped interplanetary field. Reconnection events may have occurred in the disturbed magnetic environment. Magnetic reconnection happens when oppositely directed field lines meet and reconfigure, releasing stored magnetic energy as kinetic energy of particles and plasma heating. The asymmetric field structure created by the impact plume establishes conditions favorable for reconnection. Evidence comes from the particle data showing bidirectional electron streams, a signature of reconnection temporally associated with the magnetic perturbations. If confirmed, this would mark the first observation of impact-triggered magnetic reconnection in a cometary environment. Theoretical modeling explores how long the magnetic perturbations should last. The timescale depends on how quickly the enhanced ionization decays through recombination and how fast the disturbed field configuration relaxes back to a draped state. Models incorporating realistic ionization rates and recombination coefficients predict decay timescales of 4 to 8 hours, matching the observations. This agreement strengthens confidence in our understanding of the underlying plasma physics and provides a tool for predicting magnetic responses to future cometary impacts or outbursts. Long-term magnetic monitoring continues as 3I, Atlas, moves further from the Sun. As outgassing declines with increasing heliocentric distance, the induced magnetosphere weakens. The collision's perturbations, superimposed on this secular decline, offer opportunities to study how cometary magnetic structures evolve across a wide range of gas production rates. MAVEN maintains its observation campaign, collecting data that will eventually span the comet's entire outbound trajectory through the inner solar system, creating an unprecedented magnetic field dataset for an interstellar visitor. Collision rate statistics. The detection of an impact on 3I, Atlas, invites broader questions about collision rates in interplanetary space and what this event implies for understanding the populations of small bodies throughout the solar system. Calculating expected collision frequencies requires knowledge of impactor populations, their size distributions, and orbital dynamics. Near-Earth space is relatively well characterized through asteroid surveys, but the broader solar system environment that 3I, Atlas, traverses remains less thoroughly mapped. The collision provides an empirical data point that tests and refines theoretical models. Collision probability scales with several factors, including the target's cross-sectional area, velocity relative to potential impactors, and the spatial density of objects in its vicinity. For a nucleus several kilometers across traveling at interstellar speeds through the inner solar system, theoretical models predict collision rates of order 1 impact per 1,000 years for projectiles large enough to produce observable effects. The fact that observers witnessed an impact during 3I, Atlas's brief passage through the inner solar system, suggests either significant statistical luck or that small body populations exceed baseline estimates. Size distribution of potential impactors follows a power law established from surveys and cratering statistics across the solar system. For every object 10 meters across, there exist roughly 10 times as many objects 1 meter across and 10 times fewer objects 100 meters across. This distribution, combined with observational constraints on the impactor that struck 3I, Atlas, allows inference about the size range most likely responsible. The inferred 10 to 50 meter range sits near the peak of detectability, where objects are large enough to cause visible effects, but small enough to be numerous. Spatial distribution of impactors matters critically. The main asteroid belt between Mars and Jupiter contains the solar system's largest reservoir of rocky debris. However, 3I, Atlas's perihelion inside Earth's orbit, places it outside the main belt's central region. Instead, the relevant population consists of near-Earth objects and dormant comets that cross the inner solar system. Surveys have catalogued tens of thousands of such objects larger than 100 meters, but completeness drops rapidly at smaller sizes. The collision with 3I, Atlas, adds a data point constraining the population between 10 and 50 meters, a size regime where surveys remain incomplete. Comparison with other observed cometary impacts provides statistical context. The collision of Comet Shoemaker-Levy 9 with Jupiter stands as the most spectacular recorded impact, but Jupiter's gravitational focusing makes it an unusually frequent target. More relevant are the few documented cases of small objects striking active comets, including suspected impacts on comets that produced anomalous brightness outbursts similar to what 3I Atlas experienced. The cumulative record suggests impact rates consistent with theoretical expectations, though large uncertainties remain due to the small sample size. Implications for spacecraft hazard assessment arise from this collision. Multiple missions to comets and asteroids operate or are planned, and the collision rate experienced by 3I Atlas informs risk calculations for these missions. If the observed impact represents typical conditions, then spacecraft spending months in proximity to active comets face measurable, though still low, probability of encountering debris. Mission planners incorporate such statistics into their safety protocols, balancing scientific objectives against impact risks to spacecraft systems. The interstellar nature of 3I Atlas adds unique considerations. As it entered the solar system from interstellar space, did it bring along a debris cloud of smaller fragments traveling on similar trajectories? If so, the impactor might have been a companion fragment rather than a native solar system object. This scenario would imply that interstellar visitors arrive not as isolated bodies, but as part of dispersed swarms, where collisions among family members occur with enhanced probability. Distinguishing this possibility from collision with solar system debris requires detailed trajectory analysis that traces both objects' orbits backward in time. Statistical analysis of the impact timing relative to perihelion passage reveals potential biases. The collision occurred in the post-perihelion phase, when 3I Atlas was under intensive observational scrutiny by multiple facilities. Had the impact occurred months earlier or later, when monitoring was less comprehensive, it might have gone undetected or been attributed to spontaneous outbursts rather than collision. This observational selection effect means the detected impact rate may underestimate the true rate, since many impacts at other times could have been missed. Correcting for this bias requires modelling observational coverage as a function of time throughout the comet's apparition. Future surveys targeting small body populations will benefit from incorporating this event into their statistics. Each detected collision, especially when impactor size and composition can be constrained, helps calibrate population models. As survey capabilities improve, particularly with facilities like the Vera Rubin Observatory beginning full operations, the rate of detected collisions on comets and asteroids should increase. Building a statistical sample large enough to test population models rigorously. The 3I Atlas impact represents an early data point in what will hopefully become a growing dataset. Thermal imaging analysis. Infrared observations following the collision reveal the thermal consequences of impact heating and fresh ice exposure. Thermal imaging from ground-based observatories equipped with infrared cameras and space-based platforms like the James Webb Space Telescope's mid-infrared instrument track temperature distributions across the coma. These observations detected localized hotspots coinciding with the impact location, where temperatures temporarily exceeded 300 Kelvin, well above the ambient 200 Kelvin typical of the pre-impact surface at 3I Atlas's heliocentric distance. The hotspot's temporal evolution provides diagnostic information about heat diffusion and surface properties. Peak temperature occurred approximately 1 hour after optical detection of the impact, indicating that thermal radiation took time to equilibrate following the initial shock heating. The temperature then decayed exponentially with a thermal time constant of roughly 4 hours. This timescale relates to the surface's thermal inertia, a measure combining thermal conductivity, density, and specific heat capacity. Comparing observed decay rates with laboratory measurements of these properties for various ice and rock mixtures constrains the surface composition and structure. Thermal modeling of the impact event reconstructs the heating process. Hypervelocity impacts convert kinetic energy into heat through shock compression and decompression. For the inferred impactor size and velocity, models predict instantaneous temperatures exceeding several thousand Kelvin at the impact point, sufficient to vaporize and ionize rock and ice. This extreme heating lasts only microseconds in the immediate impact zone. But waste heat diffuses into surrounding material, creating a broader region of elevated temperature that persists for hours. Matching observed temperature distributions and decay rates to model predictions confirms the impact energy estimates derived independently from optical observations. Spatial resolution of thermal imaging, though limited by the comet's distance and the telescope's capabilities, reveals asymmetry in the temperature distribution around the impact site. The hot region extends preferentially in one direction, suggesting either asymmetric ejecta deposition or the presence of pre-existing topography that channeled heat flow. High thermal inertia material, like rock, retains heat longer than low thermal inertia material like fluffy ice, creating temperature gradients that persist as different surface materials cool at different rates. These gradients appear in the data as patchy thermal structures that evolve over the rotation period. Comparison between thermal and optical observations identifies regions of the coma where dust concentration and temperature correlate or anti-correlate. Some bright regions in optical images correspond to cool regions in thermal infrared, indicating high concentrations of small, reflective dust grains that efficiently scatter sunlight but radiate poorly in the infrared. Conversely, some optically dim regions show enhanced thermal emission, suggesting larger, darker particles that absorb sunlight effectively and re-radiate at infrared wavelengths. These patterns map out particle size distributions spatially across the coma, revealing how the collision ejected material of different sizes into different directions. Sublimation physics complicates thermal interpretation. Fresh ice exposed in the crater sublimates when heated by sunlight, absorbing latent heat and cooling the surface below what pure radiative heating would produce. Thermal models must account for this cooling effect to match observations. The balance between solar heating, radiative cooling, and sublimative cooling determines the surface temperature distribution. Observations show that regions of enhanced water emission, identified spectroscopically, correlate with cooler temperatures in thermal imaging, confirming that active sublimation efficiently removes heat and regulates surface temperature. Long-wavelength thermal observations from radio telescopes provide complementary information. The sub-millimeter spectrum contains emission from dust grains at various temperatures throughout the coma's depth. By observing at multiple wavelengths, researchers reconstruct temperature profiles as a function of distance from the nucleus. Post-impact observations reveal that the temperature gradient steepened compared to pre-impact conditions, with a hotter inner coma and cooler outer regions. This steepening reflects enhanced heat source at the nucleus due to the impact combined with adiabatic cooling as material expands outward at higher velocities than before. Infrared spectroscopy adds chemical context to thermal measurements. Thermal emission features from carbon dioxide ice appear in the near-infrared spectrum at wavelengths where carbon dioxide absorption bands create characteristic signatures. The strength of these features correlates with temperature, allowing simultaneous determination of composition and temperature. Post-impact spectra show enhanced carbon dioxide emission from warmer than background regions, confirming that the impact exposed carbon dioxide-rich ice layers consistent with spectroscopic composition measurements discussed earlier. Thermal inertia mapping across the nucleus's surface will eventually emerge from accumulated thermal observations over multiple rotation periods. Different surface regions with different thermal properties will exhibit characteristic heating and cooling curves as they rotate in and out of sunlight. The impact site, with freshly excavated material, should show a different thermal response than undisturbed regions. Building such maps requires extensive data accumulation, but promises to reveal heterogeneity in surface properties that ground truth, compositional, and structural models. The collision inadvertently created a controlled experiment where human-scale thermal properties can be studied directly through remote sensing. Fragmentation risk modeling. Assessing whether 3I Atlas faces imminent fragmentation risk requires integrating data on structural integrity, thermal stresses, and outgassing pressures. Fragmentation models developed for solar system comets provide the theoretical framework. These models consider tensile strength of nucleus material, thermal gradients that create mechanical stress, and gas pressure in subsurface cavities that can fracture overlying layers. Applying these models to 3I Atlas involves accounting for its unique properties, particularly its unusual composition and the additional perturbation from the recent impact. Tensile strength estimates vary widely depending on assumed porosity and cohesion. Laboratory measurements on ice samples at temperatures and pressures relevant to cometary conditions yield strengths from 10 to several hundred kilopascals. Adding rock and dust changes these values depending on whether rocky material provides structural reinforcement or acts as weak inclusions that concentrate stress. For 3I Atlas, the straitjets suggest some structural coherence, arguing for the higher end of the strength range, but definitive measurements await future missions that can directly probe the surface. Thermal stress calculations evaluate whether heating from the impact or from solar radiation can fracture the nucleus. Thermal expansion coefficients differ between ice and rock, so heterogeneous material experiences differential expansion when heated. If temperature gradients exceed critical values, the resulting stress exceeds tensile strength and fractures propagate. Models incorporating 3I Atlas's heliocentric distance, surface albedo, and thermal properties predict stresses peaking near 100 kilopascals on the sunward side at perihelion. This approaches estimated tensile strengths, suggesting that thermal fracturing is plausible, especially if the impact weakened local structural integrity. Gas pressure buildup beneath low permeability surface layers offers another fragmentation mechanism. As solar heating penetrates beneath the surface, it sublimates ice in the interior. If overlying material has low permeability, sublimated gas accumulates, building pressure. When pressure exceeds the tensile strength times the layer thickness, the overburden fractures and explosive gas release occurs. Evidence for this mechanism comes from observed cometary outbursts where brightness increases suddenly by factors of 10 or more. For 3I Atlas, the crater created by impact may relieve some gas pressure by providing a vent, actually reducing fragmentation risk in nearby regions, while potentially increasing it elsewhere if subsurface pathways redirect gas flow. Historical fragmentation rates for observed comets provide empirical context. Surveys show that several % of Jupiter family comets undergo observable splitting events each apparition. Long-period comets show lower rates, possibly because they spend less time near the Sun where thermal stress peaks. Interstellar objects, with only Oumuamua and Borisov as precedents, offer insufficient statistics. Neither fragmented during their observed passages, though both exhibited unusual properties that set them apart from typical comets. Whether 3I Atlas follows this resilience or breaks apart depends on its specific structural characteristics, still imperfectly known. Rotational stability analysis considers whether the impact altered spin state enough to induce stress. A nucleus spinning too fast experiences centrifugal stress that can overcome tensile strength, leading to rotational breakup. The threshold spin period depends on size, density, and strength. For 3I Atlas, with its measured 16-hour period, calculations show it rotates well below the breakup limit for any reasonable strength assumptions. Even if the impact changed spin rate by 10%, the nucleus remains safely below critical spin. Rotational breakup thus appears unlikely unless strength is far lower than expected. Detailed finite element analysis simulations model fragmentation onset and propagation. These simulations discretize the nucleus into millions of elements and apply realistic material properties, thermal loads, and gas pressures. Running simulations forward in time reveals whether fractures grow and connect, or whether stress relief mechanisms prevent catastrophic failure. Preliminary results for impact-damaged nuclei show that fractures typically remain localized unless the nucleus is already near critical due to other stresses. For 3I Atlas simulations suggest the impact created local cracks, but not conditions for immediate global fragmentation. However, as the comet continues outbound and thermal conditions evolve, delayed fragmentation remains possible. Observational predictions based on fragmentation models guide monitoring strategies. If fragmentation is imminent, precursor signs include accelerating brightness changes, appearance of distinct multiple brightness peaks in the light curve, and changes in tail morphology as fragments separate and develop independent tails. Observers watch for these signatures, particularly during the months following the impact when fractures have had time to propagate, but the nucleus remains close enough to the Sun for continued observations. Detection of fragmentation in progress would provide unprecedented real-time data on breakup physics applicable to understanding asteroid disruption and planetary defense scenarios. Risk mitigation for future spacecraft missions depends on understanding fragmentation physics. If missions to interstellar objects become feasible, the risk of arriving at a fragmenting target must be assessed. A nucleus breaking apart creates hazardous debris fields that spacecraft must navigate. The 3I Atlas impact and its consequences provide a case study for such scenarios, informing mission design decisions about proximity operations, instrument pointing strategies, and contingency planning for rapidly evolving target states. Lessons learned here will shape the architecture of future interstellar object rendezvous missions. Observational challenges and limitations. Despite unprecedented coordination, observing the collision and its aftermath tested the limits of ground-based and space-based astronomy. Light travel time introduced fundamental constraints. Even at 3I, Atlas's relatively close approach, light from the comet took several minutes to reach Earth, meaning observers saw events minutes after they occurred. For rapid phenomena like the collision's immediate aftermath, this delay prevented real-time control or adaptive observation strategies. By the time data arrived and were processed, conditions had already evolved, requiring predictions about what might happen next to guide follow-up observations. Weather and sky conditions imposed additional constraints on ground observations. Sites around the globe coordinated to provide continuous coverage, but clouds blocked critical observations at some locations during key phases. The collision's timing happened to coincide with poor weather in Hawaii, eliminating one of the world's premier observatory sites from the immediate response. Southern Hemisphere facilities picked up coverage, but gaps still occurred. This experience reinforces the value of distributed observing networks where multiple sites provide backup against local weather failures. Dynamic range challenges plagued imaging efforts. The bright inner coma outshone the nucleus by factors of 10,000 or more, making detection of faint features difficult. Observers employed sophisticated image processing, including median filtering and unsharp masking, to suppress the bright core and reveal faint jets and debris structures. However, these techniques introduce artifacts, and distinguishing real features from processing artifacts requires care. Some reported features in early post-impact images later proved to be artifacts, requiring retractions and emphasizing the need for robust validation procedures. Spectroscopic signal strength, limited chemical composition studies. Even with 8 to 10 meter class telescopes, integration times of hours were required to achieve signal-to-noise ratios sufficient for detecting faint emission lines from trace species. During these long integrations, the comet rotated and conditions changed, meaning spectra represented time averaged rather than instantaneous composition. This averaging smeared out rapid temporal variations and made it difficult to isolate collision-specific signatures from background outgassing. Higher spectral resolution instruments that could have resolved subtle features required even longer integration times, creating a trade-off between spectral detail and temporal resolution that observers navigated with varying strategies. Coordinate system ambiguities complicated data interpretation across observing platforms. Different facilities used different reference frames, some heliocentric, others geocentric, and converting between these systems while accounting for light travel time and the comet's motion required careful bookkeeping. Early analyses suffered from coordinate errors that misaligned features between datasets from different telescopes. Resolving these discrepancies consumed days of effort, delaying scientific conclusions. The experience highlighted the need for standardized coordinate protocols in multi-facility campaigns targeting fast-evolving phenomena. Spacecraft pointing limitations affected space-based observations. Instruments like MAVEN and Hubble required advanced scheduling for target acquisition and could not respond instantly to the unexpected collision. By the time observation requests propagated through mission operations chains and spacecraft executed pointing maneuvers, hours had elapsed. This delay meant that some optimal observation windows were missed entirely, and datasets contained temporal gaps at critical moments. Future missions with more autonomous targeting capabilities could respond faster, but current infrastructure imposes latency that fundamentally limits rapid response science. Background contamination from field stars and galaxies introduced photometric uncertainties. At 3I, Atlas's position in the sky, multiple faint stars fell within the comet's extended coma as seen from Earth. Subtracting these stellar contributions from brightness measurements required careful astrometry to identify which point sources were stars and which might be cometary features. In some images, alignment errors caused incomplete star subtraction, creating artificial brightness fluctuations that mimicked real temporal variations. Distinguishing genuine changes from these artifacts demanded comparison across multiple independent datasets and required statistical rigor that stretched analysis timelines. Resolution limits prevented direct nucleus imaging. Even at closest approach, the nucleus subtended less than 1 arc-second as seen from Earth, below the diffraction limit of most telescopes, even with adaptive optics. Space telescopes, like Hubble, achieve better resolution, but still could not resolve the nucleus cleanly given the overwhelming brightness of the surrounding coma. This inability to see the nucleus directly meant that inferences about its shape, size, and surface features relied on indirect methods like light curve inversion and modeling. introducing model-dependent uncertainties into all size and shape determinations. Instrument saturation posed problems during the collision's peak brightness. Some detectors, optimized for the comet's pre-impact brightness, saturated when the sudden brightness increase exceeded their dynamic range. Saturated pixels provide no useful data, creating holes in the temporal coverage at the most interesting moments. Observers attempted to compensate by using shorter exposure times or neutral density filters, but these adjustments took time to implement. The resulting dataset contains gaps and varying sensitivity across different observation epochs, complicating quantitative comparisons and requiring sophisticated data calibration procedures. Atmospheric seeing degraded ground-based image quality. Even at excellent sites, atmospheric turbulence blurred images to resolutions of half an arcsecond or worse. Adaptive optics systems partially corrected for seeing, but these systems worked best on bright targets and struggled with the comet's diffuse, extended nature. The resulting image quality varied unpredictably throughout observation sequences as seeing conditions changed. Quantitative measurements of jet positions and brightnesses carried uncertainties dominated by seeing variations, and only by averaging over many frames could observers achieve the precision needed for detecting subtle effects. Data volume management challenged analysis teams. High-cadence imaging campaigns generated terabytes of raw data, requiring storage, processing, and archival. Not all institutions possessed computational infrastructure to handle these volumes efficiently, leading to processing bottlenecks. Some data sat unprocessed for days or weeks after acquisition, delaying scientific results. The experience demonstrated that observational capability has outpaced data analysis infrastructure at many facilities, and future campaigns targeting rapidly evolving phenomena need investment in computational resources comparable to investment in telescopes themselves. Coordination across time zones tested international collaboration, with observers distributed globally. Achieving real-time communication required someone to be awake at all hours. Fatigue among team members led to communication lapses and occasional duplication of effort as different groups pursued similar analyses without full awareness of each other's work. Establishing clear communication protocols and designating coordination roles helped mitigate these issues, but perfect coordination remained elusive. The experience offers lessons for future campaigns requiring sustained around-the-clock operations over extended periods. Publication pressures created tension between speed and rigor. The high-profile nature of the event incentivized rapid publication to establish priority, but the complex data required careful analysis to avoid errors. Some teams rushed preliminary results that later required correction, damaging credibility. Others held back publication until comprehensive analysis was complete, risking being scooped by faster competitors. Navigating this tension strained teams and highlighted broader issues in scientific publishing culture around balancing timely dissemination with thorough vetting. The community continues debating appropriate standards for rapid response science in the age of immediate global communication. Comparative analysis with Oumuamua and Borisov. The collision on 3I, Atlas, invites comparison with its two interstellar predecessors, providing context for understanding how typical or anomalous this event appears within the emerging class of interstellar visitors. Oumuamua, discovered in October 2017, passed through the inner solar system without detected outgassing or coma formation, leading to extensive debate about its composition and nature. No impacts were observed on Oumuamua, though its rapid discovery to departure timeline left limited observation windows. Its inferred elongated shape and tumbling rotation state differed markedly from typical cometary nuclei, and the non-gravitational acceleration it experienced remains contentious. Borisov, detected in August 2019, presented a more conventional cometary appearance with active outgassing, a visible coma, and spectroscopic signatures of familiar molecules like water and carbon monoxide. Throughout its perihelion passage, Borisov exhibited behavior largely consistent with solar system comets, aside from its hyperbolic orbit confirming interstellar origin. No impacts were detected on Borisov either, though its observation campaign was less intensive than what 3I Atlas has received. The composition measurements showed carbon monoxide abundances several times solar system norms, hinting at formation in colder conditions than our own protoplanetary disk. 3I Atlas occupies an intermediate position between these two extremes. Like Borisov, it displays active outgassing and cometary appearance, but its composition shows even greater carbon monoxide enrichment and unusual metal content, unlike either predecessor. The straightjets represent a morphological anomaly not observed in Borisov, which showed conventional curved jets matching rotational expectations. The collision detection on 3I Atlas has no parallel in either earlier case, though this may reflect observational coverage rather than intrinsic differences in collision rates experienced by the three objects. Size comparisons reveal diversity among interstellar visitors. Oumuamua's inferred dimensions placed it in the 100-meter size class, much smaller than typical cometary nuclei. Borisov's nucleus measured approximately 1 kilometer across, typical for solar system comets. 3I Atlas falls in the 1 to 5 kilometer range, making it the largest of the three confirmed interstellar objects. This size difference affects collision probability through geometric cross-section, with 3I Atlas presenting a larger target. However, all three experienced the same background impactor population during their passages, so the collision detection on 3I Atlas may simply reflect longer observation duration and more intensive monitoring. Rotation periods show interesting patterns. Oumuamua's tumbling period of approximately 8 hours suggested either a highly elongated shape or excitation from some torque source. Borisov's rotation remained poorly constrained due to lower brightness and observational challenges, with estimates ranging from 4 to 24 hours. 3I Atlas's well-determined 16-hour period falls in the typical range for cometary nuclei, suggesting conventional spin properties. The impact on 3I Atlas provides an opportunity to measure how collisions affect rotation, a measurement impossible for the other two objects given no detected impacts. Compositional diversity across the three objects hints at varied formation environments or evolutionary histories. Oumuamua's lack of detected volatiles, if confirmed rather than observational limitation, implies either extreme depletion or non-cometary composition. Borisov's composition resembled solar system comets, but with enhanced carbon monoxide. 3I Atlas pushes further into chemical territory, unlike our native objects, with its extreme carbon monoxide dominance and unusual metal content. Whether this progression represents real diversity in interstellar comet compositions or observational selection effects remains unclear, but it suggests that interstellar space contains a wider variety of small body types than our solar system alone displays. Trajectory comparisons reveal different dynamical histories. Oumuamua arrived from the direction of the constellation Lyra with incoming velocity around 26 kilometers per second. Borisov came from Cassiopeia at approximately 32 kilometers per second, a 3I. Atlas approaches from yet another direction with velocity around 23 kilometers per second. The divergent arrival directions confirm that these are independent objects rather than fragments from a common parent body. Tracing trajectories backward through the galaxy using kinematic models suggests different stellar neighborhoods of origin, though pinpointing specific source stars remains impossible, given uncertainties in galactic motion over the millions of years these objects spent in interstellar space. Observational circumstances differed significantly among the three cases. Oumuamua was discovered post-perihelion and receding rapidly, limiting observation windows to weeks. Borisov was discovered pre-perihelion, allowing months of monitoring through perihelion passage and beyond. 3I, Atlas, benefits from even earlier discovery and favorable geometry, enabling the most comprehensive observation campaign yet conducted on an interstellar visitor. This progressive improvement in observational capability means that apparent differences between objects may partly reflect detection and monitoring improvements rather than intrinsic object differences. The impact detection on 3I, Atlas, sets a precedent that informs predictions for future interstellar visitors. If collision rates inferred from this single detection represent typical conditions, then future objects monitored with similar intensity should experience observable impacts at rates of order unity per perihelion passage. This prediction can be tested as additional interstellar comets are discovered and monitored, gradually building statistics on collision rates and their effects. Each new interstellar visitor refines our understanding of both the objects themselves and the environment through which they travel. Public and scientific interest levels varied across the three objects. Oumuamua generated enormous public attention and scientific debate due to its unusual properties and the suggestion by some researchers of possible artificial origins. Borisov attracted less public notice, despite being the first clearly cometary interstellar object, perhaps suffering from second object syndrome. 3I Atlas appears to be generating renewed public engagement, particularly following the collision detection and the continuing mysteries of its straight jets. Media coverage patterns suggest that anomalies and dynamic events drive public interest more than steady, well-understood behavior, a factor that shapes funding priorities and scientific attention allocation in ways that may not always align with objective scientific importance. Trajectory modification and future path. The collision's momentum transfer raises questions about whether 3I, Atlas's trajectory, has been measurably altered. Precise astrometric measurements before and after the impact provide the data needed to detect changes. Positional measurements with sub-arc-second precision from multiple observatories allow calculation of the comet's skyplane position and motion. Any deviation from the predicted ephemeris computed from pre-impact observations would indicate that the collision imparted sufficient momentum to change the orbital elements detectably. Initial analysis shows no obvious trajectory change within measurement uncertainties. The comet's observed position continues to match predictions based on pre-impact orbital elements to within a few arc-seconds, comparable to positional uncertainties. However, velocity changes too small to affect position noticeably over days or weeks could still accumulate into larger deviations over months. Long baseline astrometry, extending months into the future, will eventually reveal whether subtle trajectory changes occurred, potentially constraining the impactor's mass and collision geometry through their effect on the nucleus's motion. Orbital element changes of interest include semi-major axis, eccentricity, and inclination. The semi-major axis determines orbital energy, eccentricity describes orbit shape, and inclination measures tilt relative to the ecliptic plane. The collision could theoretically alter any or all of these elements depending on impact, direction, and magnitude. For typical impact parameters, theoretical calculations predict changes in the parts per million range, below current measurement precision but potentially detectable with extended monitoring and careful error analysis. Non-gravitational forces complicate trajectory analysis. Cometary outgassing creates rocket-like thrust that alters orbits independently of collisions. Separating collision-induced changes from outgassing effects requires modeling both processes. The well-characterized pre-impact outgassing provides a baseline that can be extrapolated forward and compared against observed motion. Deviations from this extrapolation could indicate collision effects, but disentangling the two requires detailed gas production rate measurements and knowledge of the jet thrust vectors, both uncertain. Future predictions for 3I, Atlas's path, show it departing the solar system on a hyperbolic orbit, never to return. Even if the collision modified its trajectory, the changes are too small to convert the orbit from hyperbolic to elliptical. The object will continue outbound, crossing Earth's orbit in the coming months and eventually departing beyond Neptune within a few years. Visibility from Earth will decline as distance increases and solar illumination weakens, setting a practical limit on how long observations can continue. Within a decade, 3I Atlas will be too faint for any existing telescope to detect. Potential future impacts remain a possibility as the comet traverses regions of varying impactor density. The asteroid belt, which 3I Atlas has already passed, represents a region of enhanced collision probability. Moving outbound through the outer solar system, impactor density drops substantially, making further collisions less likely, but not impossible. The Kuiper belt beyond Neptune's orbit contains a vast reservoir of small icy bodies, but 3I Atlas's trajectory will carry it through relatively sparse regions. Probabilistic calculations suggest further detectable impacts are unlikely, but statistical uncertainties mean surprises remain possible. Comparison with long-period comets from the Oort cloud shows that 3I Atlas's fate will mirror these distant relatives more than the Jupiter family comets that dominate near-Earth cometary activity. Long-period comets make single passages through the inner solar system and depart, often never returning on human timescales. 3I Atlas follows this pattern, but with the additional distinction of never having been bound to the Sun. Its outbound journey returns it to interstellar space, where it will drift for millions or billions of years until perhaps encountering another stellar system's gravitational influence. The possibility of 3I Atlas encountering other stars in the galactic neighborhood invites speculation. Kinematic models tracing its galactic orbit forward show closest approaches to several nearby stars over the next few 100,000 years, but close in this context means light years. The probability of capture into orbit around another star is minuscule given the vast distances and low velocities involved. More likely, 3I Atlas will remain in interstellar space indefinitely, gradually cooling and ceasing active outgassing as it moves beyond the influence of stellar heating, eventually becoming a dark, dormant body drifting through the galactic background. The scientific legacy of 3I Atlas's trajectory extends beyond its own motion. Each interstellar visitor refines understanding of the local interstellar medium's properties and the galactic neighborhood's structure. The convergence of trajectories from Oumuamua, Borisov, and 3I Atlas, traced backward through time, probes galactic kinematics and tests models of how stellar systems move relative to each other. Over time, as more interstellar objects are discovered and their trajectories measured, a three-dimensional picture of the local galactic environment will emerge, with implications for understanding stellar formation history and galactic dynamics. Planetary defense implications arise from trajectory studies of interstellar visitors. Though none of the three known interstellar objects posed impact hazards to Earth, future visitors could arrive on collision courses. Understanding how to detect and track interstellar objects informs preparedness for potential threats. The collision on 3I Atlas demonstrates that these objects can experience impacts while passing through the solar system, adding complexity to threat assessment scenarios. A hazardous interstellar object that suffers fragmentation from collisions becomes multiple threats requiring tracking, a complication for mitigation planning. Plasma physics implications. The collision on 3I Atlas created a natural laboratory for studying plasma physics under conditions difficult to replicate terrestrially. The sudden injection of neutral gas into the existing plasma environment triggered a cascade of ionization, charge, exchange, and electromagnetic interactions observable by spacecraft and ground-based facilities. Theoretical plasma physicists seized on the event to test models of non-equilibrium plasma behavior, magnetic field generation, and particle acceleration mechanisms in rarefied environments. Ionization mechanisms operating in the post-impact environment include photoionization by solar ultraviolet radiation, charge exchange with solar wind ions, and electron impact ionization. Each process operates on different timescales and produces different ion velocity distributions. Photoionization creates low-energy ions moving at speeds close to the neutral gas from which they formed. Charge exchange generates ions with velocities matching the solar wind, around 400 km per second. Electron impact produces hot ions with energies of tens of electron volts. The observed ion populations, measured by MAVEN's particle detectors, show signatures of all three processes, with relative contributions evolving as the debris cloud expanded and densities decreased. Two-stream instabilities developed where freshly created cometary ions moving slowly encountered the fast-flowing solar wind. When two populations of charged particles with different bulk velocities coexist, electromagnetic instabilities can grow, generating waves that scatter particles and redistribute energy. Spacecraft measurements detected enhanced wave power at frequencies characteristic of ion acoustic and magnetosonic modes immediately following the impact. These waves, while weak by laboratory standards, efficiently transferred energy from the solar wind to cometary ions, heating them and accelerating some to high velocities observed in the particle data. Ambipolar electric fields established themselves as the debris cloud ionized. When electrons, being much lighter than ions, attempted to escape faster from the cloud, their departure created a charge separation that generated electric fields, pulling electrons back and pushing ions outward. This ambipolar field accelerates ions to velocities exceeding what thermal pressure alone would produce. Observations of ion velocity distributions showed high energy tails consistent with ambipolar acceleration, confirming theoretical predictions. The magnitude of the acceleration depends on electron temperature and ion mass, with lighter ions like hydrogen accelerated more than heavier species like oxygen or carbon dioxide. Magnetic field draping, already present before impact, intensified as ion production increased. The interplanetary magnetic field, carried by the solar wind, cannot penetrate regions of high electrical conductivity, so it drapes around the ionized coma. The increased ionization from the impact enhanced this draping effect, creating a sharper boundary between the magnetized solar wind and the partially ionized coma. Magnetometer data showed the draping region's extent increased by roughly 20,000 kilometers following the impact, then gradually contracted as the debris dispersed and ion density decreased. Current systems formed to maintain magnetic field continuity across the ionized region's boundary. Electric currents flowing perpendicular to magnetic field gradients support the pressure balance between magnetic and plasma thermal pressures. Maven's magnetometer detected these boundary currents indirectly through their magnetic signatures. The current density, estimated at nanoamperes per square meter, while tiny by terrestrial standards, flows over areas of billions of square kilometers, representing total currents of millions of amperes. These currents closed through the solar wind and the ionosphere-like region surrounding the nucleus, forming a complete circuit. Wave-particle interactions accelerated a fraction of ions to energies far exceeding thermal values. The observed power law energy spectra, extending to kilo-electron-volt energies, require acceleration mechanisms beyond simple heating. Candidate processes include resonant interaction with plasma waves, stochastic acceleration in turbulent fields, and shock acceleration if shocks formed in the flow. Distinguishing among these mechanisms requires detailed comparison between wave and particle measurements, analysis still underway. The accelerated ion population, while small in number, carries significant energy and contributes disproportionately to the overall energy budget of the plasma environment. Recombination processes partially offset ionization, establishing equilibrium ion densities lower than if all produced ions remained ionized indefinitely. Radiative recombination, where free electrons capture onto ions and emit photons, proceeds slowly in the low-density coma. Dissociative recombination, where molecular ions capture electrons and dissociate into neutral atoms, occurs much faster and dominates loss rates. The balance between production and loss determines the ionization fraction, measured at roughly 1% in the densest regions of the coma and lower further out. This low ionization fraction means most of the coma's mass remains neutral, but the ionized component controls electromagnetic properties and interaction with the solar wind. Laboratory plasma experiments attempted to recreate relevant conditions after the collision. Facilities capable of producing expanding plasma clouds in vacuum chambers, with background magnetic fields and energetic particle beams simulating solar wind conditions, ran campaigns to test specific aspects of the interaction. These experiments faced challenges replicating the scale disparity between laboratory and cometary environments. Collisionless plasma behavior that dominates in the tenuous cometary coma transitions to collisional regime in denser laboratory plasmas. Despite limitations, experiments validated some theoretical predictions and revealed unexpected phenomena like secondary instabilities, cascade effects that modelers are now incorporating into simulations. Astrophysical analogues to the 3I Atlas plasma environment include supernovae remnants, planetary nebulae, and stellar wind interactions with the interstellar medium. These disparate systems share fundamental physics of expanding plasma clouds, shock formation, magnetic field generation, and particle acceleration. Insights from studying the comet's collision plasma inform interpretation of observations from these more distant and energetic systems. The accessibility and measurability of cometary plasma environments make them valuable laboratories for testing concepts relevant across astrophysics, demonstrating how solar system studies contribute to understanding phenomena throughout the universe. Contamination risk for solar system objects. The collision raises subtle questions about whether interstellar visitors could contaminate the solar system with foreign material or, conversely, whether solar system material could contaminate interstellar objects. Each collision between an interstellar visitor and a native solar system body represents potential material exchange. For 3I, Atlas, the impactor likely was a solar system asteroid or comet fragment, meaning solar system material now resides on or mixed with interstellar material. Conversely, ejecta from 3I, Atlas, escapes into interplanetary space, potentially reaching other solar system bodies. Quantifying contamination requires tracking ejected material's subsequent fate. Particles escaping 3I, Atlas, at hundreds of meters per second follow ballistic trajectories influenced by solar gravity and radiation pressure. Numerical integration of these trajectories shows that most material remains in heliocentric orbit, gradually dispersing into a torus around the Sun at distances matching 3I, Atlas's orbit. Some particles acquire velocities exceeding solar system, escape speed and depart entirely, carrying interstellar material permanently away. A small fraction of particles might eventually intersect Earth or other planets, though probabilities are minuscule given the vastness of space. Biological contamination concerns center on whether life, if present on interstellar objects, could transfer to solar system worlds. This scenario requires that interstellar visitors harbor viable organisms, that collisions eject such organisms without sterilizing them through shock heating, and that ejected material eventually reaches environments where life could survive. Each step faces enormous improbabilities. The collision's impact heating likely exceeded temperatures that any known organism could survive. Even if some material escaped unheated, radiation exposure during interplanetary transit and atmospheric entry heating create additional sterilization steps. Panspermia hypotheses invoke such transfer mechanisms, but empirical evidence remains entirely absent. Chemical contamination represents a more plausible concern. The unusual composition of 3I, Atlas, particularly its metal content and organic molecules, differs from typical solar system material. If significant quantities reached solar system bodies, chemical signatures might be detectable. However, the collision ejected at most millions of tons of material dispersed across the inner solar system's vast volume. Even optimistic estimates suggest deposition rates on Earth or other planets of micrograms per square meter over geological timescales, utterly negligible compared to natural accumulation from interplanetary dust and meteorites. Conversely, solar system contamination of interstellar objects may carry scientific implications for future studies. If humanity eventually reaches another star system and examines small bodies there, distinguishing primordial material from contamination acquired during solar system passages will be crucial. The 3I Atlas collision demonstrates that such contamination occurs, meaning future interstellar visitors to our solar system will carry traces of our local environment when they depart. Over billions of years and countless stellar encounters, interstellar objects gradually accumulate material from visited systems, creating complex compositional mixtures challenging to interpret. Planetary protection protocols developed to prevent contamination during space missions do not currently address interstellar visitor scenarios. These protocols focus on preventing Earth microbes from contaminating other solar system worlds and vice versa, assuming a closed solar system where all bodies share common origin. Interstellar visitors violate this assumption, introducing truly alien material. While collision-driven material exchange is natural and predates humanity, future scenarios might involve deliberate rendezvous missions to interstellar objects, raising questions about whether planetary protection principles should extend to preventing cross-contamination between stellar systems. Isotopic tracer studies could potentially identify interstellar contamination in solar system materials. Meteorites and interplanetary dust collected on Earth or by spacecraft undergo isotopic analysis to determine origin and history. Material from 3I, Atlas, should carry distinctive isotopic signatures reflecting its formation in a different stellar environment. If fragments ever reach Earth, their isotopic ratios would stand out from native material. Systematic searches for such anomalous grains have begun, motivated partly by interstellar visitor discoveries. Finding even a single grain of confirmed interstellar origin would revolutionize cosmochemistry and astrobiology. The collision's role in distributing material complicates source attribution for some meteorite classes. Meteorites fall into taxonomic groups based on composition and structure, with most tied to specific parent bodies like asteroid families or cometary nuclei. A small fraction of meteorites defy classification, showing compositions unlike any known solar system object. Could these be fragments of previous interstellar visitors that collided with solar system bodies and eventually reached Earth? The probability is extremely low, but non-zero. Systematic evaluation of anomalous meteorites for potential interstellar origin markers, like unusual isotopic ratios or extinct radionuclides with timescales mismatched to solar system formation, continues as a fringe but legitimate research direction. Risk assessment for future human activities in space must account for interstellar contamination possibilities. As humanity expands into resource extraction from asteroids and comets, distinguishing native from foreign material becomes economically and scientifically relevant. An asteroid targeted for mining could theoretically contain interstellar contaminants from ancient collisions, affecting resource assessment and processing strategies. While practical implications remain distant given current technology limitations, forward-thinking planning considers these scenarios when designing detection protocols and assay methods for space resource operations. Theoretical explanations for jet stability. The collision's failure to disrupt 3I, Atlas's impossibly straight jets, intensifies demands for theoretical explanations. Pre-collision, various hypotheses attempted to explain the jet morphology, but none achieved consensus acceptance. Post-collision, those same jets persist with only minor deflection, suggesting that whatever maintains their straightness operates robustly even under perturbation. Reviewing and evaluating theoretical proposals becomes more urgent as observational constraints tighten. Electrodynamic jet collimation stands as one of the more exotic proposals. If the nucleus carries electric charge or generates currents, electromagnetic forces could shape outflowing plasma into tightly collimated streams. Magnetic fields around current-carrying jets confine charged particles, and neutral molecules follow through collisions with ions in partially ionized flows. Laboratory plasma jet experiments demonstrate that magnetic collimation can produce stable, straight jets persisting over many jet diameters. Scaling this mechanism to cometary conditions requires implausible charge densities or currents, but advocates argue that unusual conditions on interstellar objects might support such phenomena. Topographic focusing proposes that deep, narrow surface fissures channel gas into highly collimated streams. Modeling shows that vertical fissures with depth-to-width ratios exceeding 10:1 produce jets with minimal divergence angles. The rotation problem remains. As the nucleus spins, fissure orientation changes, and jets should sweep out arcs. However, if multiple fissures arrayed around the nucleus activate sequentially as they rotate into sunlight, the composite structure might create the illusion of stable jets. This model predicts subtle flickering or brightness variations with the rotation period, which observers are now searching for in high-cadence data. Dust grain dynamics offers another angle. If jets contain predominantly large, millimeter-sized particles rather than micron-sized dust, radiation pressure affects them less and they follow more ballistic trajectories. simulations show that jets of large grains remain straighter than jets of small grains over the same distance. However, observations clearly show both large and small particles in 3I, Atlas's jets, and even large particles should show some divergence over million-kilometre scales. This mechanism might contribute to jet stability, but cannot fully explain the observations alone. Magnetic field topology frozen into the nucleus during formation could guide jets if fields survived interstellar transit. Some interstellar formation scenarios predict that cometary nuclei retain fossil magnetic fields from their birth environments. If such fields permeate the nucleus, outgassing material follows field lines, naturally producing straight jets aligned with field directions. The collision might have disrupted local fields, explaining the observed jet deflection, while global field structure remained intact. Testing this hypothesis requires direct magnetic field measurements near the nucleus, currently impossible but potentially achievable with future rendezvous missions. Plasma instabilities could paradoxically stabilize jets. Certain instabilities growing in jets create self-organized structures that resist perturbations. The jet effectively develops an internal structure that opposes external forces attempting to bend it. Laboratory experiments with high Mach number gas jets show that turbulence, rather than destabilizing the jet, can create coherent structures that enhance collimation. Applying this counterintuitive physics to cometary scales remains speculative, but computational fluid dynamics, including turbulence modeling, shows hints of such behavior under some parameter choices. Subsurface outgassing reservoirs with specific pressure distributions could create jets that maintain orientation independent of nucleus rotation. If gas accumulates in subsurface cavities, with pressure sufficient to drive sustained outflow through narrow vents, and if these vents remain oriented towards specific directions through structural rigidity, jets would appear stable even as the nucleus rotates. The cavity pressure must remain essentially constant throughout rotation, requiring replenishment mechanisms that balance depletion from outgassing. Models exploring this scenario find narrow parameter ranges where it works, demanding specific combinations of cavity, size, replenishment rate, and vent geometry. Compound structures where multiple jets superpose to create straight-appearing features offer a prosaic explanation. If several jets, each individually curved from rotation, happen to overlap along the line of sight from Earth, their sum might appear straight, while individual components are not. This geometric conspiracy would be orientation dependent, meaning jets should appear curved when viewed from other angles. Space-based observations from different vantage points could test this, though opportunities remain limited given spacecraft locations and pointing constraints. Some viewing angle variations have occurred as 3I Atlas moved along its orbit, and preliminary analysis suggests jets maintain straightness across these changes, arguing against simple superposition effects. Testing these theories requires observations that current capabilities struggle to provide. Magnetic field measurements near the nucleus would constrain electromagnetic models. High-resolution spectroscopy resolving jet internal structure could test fluid dynamic theories. Multi-angle imaging from widely separated vantage points would evaluate geometric explanations. Until such data become available, theoretical debates remain underdetermined by observations, with multiple models producing qualitatively similar predictions that match current data. The collision provided a natural experiment perturbing the system, and the jet's resilience narrows parameter space slightly, but definitive answers await more comprehensive observations. Amateur astronomer contributions. Amateur astronomers' contributions to 3I, Atlas science rival, or exceed some professional observatory efforts, a striking validation of distributed observational networks. The collision detection benefited enormously from coordinated amateur campaigns that maintained near-continuous monitoring across multiple continents. While professional facilities allocate observing time competitively and often focus on diverse projects, amateur networks can sustain single-target campaigns with persistence difficult for professionals to match. High-quality data from amateur systems challenges the assumption that meaningful astronomical research requires access to major observatories. Modern cameras cooled to near cryogenic temperatures, combined with precision tracking mounts and commercial image processing software, deliver performance approaching professional-grade instruments from decades past. Apertures of 20 to 40 centimeters, typical for serious amateur systems, suffice for imaging bright comets with resolution limited more by atmospheric seeing than by telescope capability. Amateurs leveraging these tools produce some of the clearest images of 3I, Atlas's jet structures. Coordination and data sharing networks like the International Comet Quarterly and various online forums enable amateurs to function as distributed observing teams. When one observer's location experiences poor weather, others elsewhere continue monitoring. Image processing expertise distributes across the community, with specialists in photometry, astrometry, or image enhancement collaborating on datasets from multiple contributors. This collaborative model yields scientific returns, exceeding what any individual could achieve, demonstrating how coordination amplifies capability. Timeliness gives amateurs unexpected advantages over some professional facilities. Without proposal cycles, review committees, or scheduling constraints, amateurs can respond to transient events within hours. When the collision was first detected, amateurs worldwide began observing immediately, while professional facilities queued observation requests through established protocols. In rapidly evolving situations, amateurs' agility provides crucial early data that shapes understanding of events before professional campaigns fully engage. Citizen science projects formalize amateur contributions, creating structures where non-professional observers contribute to professional research programs. Projects focused on comet monitoring recruit amateurs to provide regular observations that professionals incorporate into larger datasets. For 3I, Atlas, several citizen science initiatives, coordinated observation campaigns, provided standardized analysis tools, and aggregated results into formats usable by research teams. Participants receive training in proper observing techniques and data quality standards, ensuring contributed observations meet scientific requirements. Publication barriers historically prevented amateur work from reaching peer-reviewed literature, but evolving norms increasingly recognize amateur contributions. Several papers analyzing 3I, Atlas, include amateur astronomers as co-authors based on their observational contributions. Journals now routinely accept data from well-documented amateur observations when quality meets standards. This shift acknowledges that observation quality depends more on technique and equipment capability than on professional affiliation, democratizing participation in frontier research. Educational impacts flow from amateur engagement with cutting-edge science. Students and educators following amateur observation campaigns learn real-time science in action, seeing how observations inform evolving understanding. The transparency of amateur networks, where data and analysis appear publicly almost immediately, contrasts with professional research's longer publication timelines. This openness provides teaching opportunities about scientific process, showing hypothesis formation, testing, and revision as it happens, rather than as polished final products. Technology development in amateur astronomy often transfers to professional applications. Innovations in camera design, image processing algorithms, and telescope control systems frequently originate in the amateur community, where experimenters push equipment boundaries. Techniques for removing atmospheric effects, combining images from different sources, or calibrating photometric measurements see initial development by amateurs before adoption professionally. This technology flow enriches both communities and accelerates capability improvements, benefiting all observers. Limitations of amateur contributions must be acknowledged alongside achievements. Absolute photometric calibration remains challenging without access to standard star observations and professional-grade analysis pipelines. Positional astrometry at subarc-second precision requires careful calibration against reference catalogues. Spectroscopy remains largely beyond amateur capability, given the expense and complexity of spectrographs. Professional facilities retain advantages in these technical areas, making amateur-professional collaboration synergistic rather than competitive, with each contributing unique strengths. Future prospects for amateur contributions look increasingly promising. As equipment costs decline and capability improves, the performance gap between amateur and professional instruments narrows. Coordinated networks can provide temporal resolution and global coverage unattainable through individual professional observatories. For transient phenomena like the 3I Atlas collision, distributed amateur networks may represent the optimal observing strategy, delivering continuous monitoring that professional facilities cannot match despite their superior sensitivity. The collision's detection and characterization relied heavily on this distributed model, validating its effectiveness and pointing toward expanded amateur roles in future campaigns. Solar-wind interaction complexity. The collision fundamentally altered how 3I Atlas interacted with the solar wind, creating a natural experiment in plasma physics that spacecraft instruments captured in unprecedented detail. Before impact, the comet's interaction with the solar wind followed relatively predictable patterns documented in studies of solar system comets. The enhanced gas production from the collision disrupted this equilibrium, forcing researchers to reconsider assumptions about how variable outgassing affects solar wind interactions. Mass loading represents the primary mechanism through which comets affect the solar wind. As solar wind plasma flows past the nucleus, it encounters freshly ionized cometary material. These newborn ions, created through photoionization and charge exchange, initially move slowly compared to the solar wind's 400 km/s velocity. The solar wind must slow down to accommodate the added mass, converting bulk flow energy into heating and electromagnetic turbulence. Before the collision, mass loading occurred at steady rates, determined by solar-driven sublimation. The impact's sudden injection of material created a pulse of enhanced mass loading that propagated through the interaction region as spacecraft watched. Bow shock formation became temporarily more pronounced following the collision. When solar wind encounters high enough ion production rates, a bow shock forms upstream of the nucleus, where the solar wind flow abruptly slows from supersonic to subsonic speeds. Most comets lack sufficient gas production to form persistent bow shocks, but during active phases or outbursts, transient shocks can develop. The 3I Atlas collision created conditions where a weak shock structure appeared in the solar wind data, persisting for approximately 12 hours before dissipating as gas production declined. This transient shock provided opportunities to study shock physics in a controlled, natural setting. Ion pickup processes accelerated cometary ions to solar wind velocities through electromagnetic forces. Freshly created ions gyrate around the interplanetary magnetic field lines at velocities determined by the local field strength and their charge-to-mass ratio. As they gyrate, they gradually gain energy from the flowing solar wind through wave-particle interactions, eventually matching the bulk flow speed. The collision's enhanced ion production created observable populations at all stages of this pickup process simultaneously, allowing researchers to track acceleration from initial creation through final equilibration with the solar wind. Turbulence generation downstream of the interaction region showed marked enhancement following the collision. Turbulent fluctuations in magnetic field and plasma parameters increased in amplitude and extended over a broader frequency range than pre-impact conditions. Power spectral analysis revealed energy cascading from large-scale structures at ion gyration scales down to smaller electron scales, a signature of fully developed plasma turbulence. This turbulence efficiently mixed cometary and solar wind plasma, creating a hybrid population with intermediate properties. Understanding this mixing informs broader questions about how different plasma populations combine in astrophysical contexts. Ion composition measurements are distinguished between solar wind protons and various cometary ion species, including water group ions, carbon dioxide ions, and carbon monoxide ions. Mass spectrometry from spacecraft instruments resolved these populations, tracking how their relative abundances changed through the collision sequence. Initially dominated by water group ions, the composition shifted toward carbon monoxide dominance post-impact, reflecting the unusual composition of material excavated from the nucleus. This compositional evolution provided real-time chemical analysis of subsurface material exposed by the crater. Plasma boundaries around the comet sharpened and intensified following enhanced outgassing. The contact surface separating shocked solar wind from the inner coma became more distinct, with steeper gradients in density and magnetic field strength. The diamagnetic cavity, a region where magnetic fields are excluded by plasma pressure, expanded from approximately 1,000 kilometers pre-impact to nearly 10,000 kilometers at peak outgassing. Tracking these boundary motions revealed how cometary plasma structures scale with gas production rate, validating theoretical models and providing calibration data for interpreting observations of more distant comets. Energetic particle acceleration at the bow shock injected ions to energies exceeding 100 kiloelectron volts. These accelerated particles, detected by spacecraft energetic particle instruments, represent a tiny fraction of the total ion population, but carry disproportionate energy. Acceleration mechanisms likely involved repeated shock crossings, as turbulence and magnetic field variations allowed particles to scatter back and forth across the shock front, gaining energy with each crossing. The efficiency of this acceleration process depends on shock, strength, and geometry, parameters that varied throughout the collision event and provided opportunities to test acceleration theories under changing conditions. Time-dependent simulations reproduced many observed features when driven by realistic gas production profiles derived from optical observations. Researchers input the measured brightness changes into magnetohydrodynamic codes to predict plasma behavior, then compare predictions against spacecraft measurements. Agreement was generally good, validating the simulation codes and demonstrating that the essential physics is captured in current models. Discrepancies highlighted areas where model refinements are needed, particularly regarding small-scale turbulence and kinetic effects not fully captured in fluid approximations. Long-term monitoring as the collision's effects faded provided insights into relaxation timescales and memory effects in cometary plasma environments. The interaction region did not instantly return to pre-impact conditions but relaxed gradually over days as enhanced gas production decayed and plasma structures readjusted. Some effects, like the modified magnetic field draping pattern, persisted longer than others. indicating that large-scale electromagnetic structures have longer memory than local density enhancements. These varying timescales inform predictions about how cometary plasma environments respond to natural variability in outgassing rates, communication, and data dissemination. The speed at which collision data reached the global scientific community tested communication infrastructure and established precedent for rapid information sharing during transient events. Initial detection notices propagated through established alert networks, including the Transient Name Server and the Central Bureau for Astronomical Telegrams, within hours of first observation. These systems, designed for supernova and other transient discoveries, adapted readily to the cometary impact scenario, demonstrating their versatility for unexpected events. Social media accelerated unofficial information dissemination, with astronomers tweeting images and preliminary analyses even before formal publications appeared. This real-time science communication engaged public audiences immediately, but created challenges when early interpretations required revision. The tension between sharing exciting developments quickly and maintaining accuracy remained unresolved, with different researchers adopting different communication strategies. Some embraced immediate public engagement, while others preferred waiting for peer review, reflecting broader debates about science communication practices in the digital age. Data repositories played crucial roles in making raw observations accessible. Major observatories deposited processed images and calibration data into public archives within days of acquisition, much faster than typical publication timelines. This open access enabled independent researchers worldwide to conduct analyses without waiting for published papers, accelerating the pace of discovery. Amateur astronomers also shared data through community platforms, creating distributed archives that complemented official repositories. The combination of professional and amateur data streams produced comprehensive coverage that no single source could match. Preprint servers like RxIve received a flood of papers analyzing the collision, with multiple groups rushing to publish first results. This rapid publication culture has benefits and costs. It speeds knowledge dissemination and enables real-time peer discussion as researchers comment on preprints before formal review. However, it also perpetuates pressure to publish quickly, potentially at the expense of thoroughness. Several early preprints required corrections or retractions when more complete data revealed errors, highlighting risks of excessive speed in scientific publication. International coordination across time zones facilitated continuous analysis as the collision's effects evolved. When researchers in one hemisphere slept, colleagues elsewhere continued work, creating effective 24-hour coverage. Virtual meetings and messaging platforms enabled real-time collaboration despite geographic separation, with shared documents and data repositories ensuring everyone worked from consistent information. This global coordination represented the triumph of modern communication technology applied to scientific research, enabling cooperation at scales previously impossible. Language barriers occasionally impeded information flow, particularly when important observations came from non-English speaking observers. Automatic translation tools helped, but sometimes introduced ambiguities or errors in technical terminology. Multilingual scientists who could bridge language gaps became invaluable, facilitating communication between research groups that otherwise might have remained isolated. The experience highlighted the importance of language diversity in science and the need for better translation tools adapted to specialized technical vocabulary. Proprietary data concerns arose when some observatories withheld high-resolution images pending publication by their teams. While data protection for limited periods allows observers to conduct thorough analysis and earn publication credit for their efforts, Excessive proprietary holds can slow scientific progress on rapidly evolving phenomena. Debates about appropriate proprietary periods for transient event data remain contentious, with community norms varying between subdisciplines. The collision forced some of these tensions into the open as researchers negotiated data-sharing agreements to enable comprehensive analysis. Educational outreach leveraged the collision's public interest to communicate broader lessons about comets, interstellar visitors, and scientific process. Planetariums, science museums, and educational websites produced content explaining the event in accessible terms. The availability of amateur images at various quality levels provided teachable moments about how scientific knowledge builds from multiple sources with varying capabilities. Educators emphasized that science involves progressive refinement of understanding rather than immediate perfect knowledge, using the collision's unfolding story to illustrate an iterative scientific process. Long-term archival considerations ensure that collision data remain accessible for future researchers who may approach analysis with new techniques or theoretical frameworks. Digital preservation challenges include format obsolescence, storage media degradation, and maintaining documentation that makes archived data interpretable decades later. Professional archives implement strategies addressing these challenges, but amateur data face higher preservation risks. Community-driven archival projects attempt to capture and preserve amateur observations, recognizing their scientific value and vulnerability to loss. Instrument performance under extreme conditions. The collision tested astronomical instruments under conditions they rarely encounter, pushing some to their performance limits and revealing capabilities and limitations not apparent during routine operations. High-cadence imaging required rapid detector readout cycles that stressed electronics and thermal management systems. Cameras designed for single exposures every few minutes operated continuously for hours, accumulating heat that degraded image quality until cooling systems caught up. Engineers monitored instrument health closely, occasionally pausing observations to allow thermal equilibration, balancing science objectives against hardware protection. Photometric saturation plagued bright object observations when the comet's enhanced brightness exceeded detector dynamic range. Saturated pixels provide no useful quantitative information, creating gaps in light curve coverage during the brightest phases. Observers attempted to compensate using neutral density filters or shorter exposures, but these adaptations required time to implement and often came too late to capture peak brightness. Future transient monitoring campaigns should incorporate automatic exposure adjustment to handle sudden brightness changes without manual intervention. Spectroscopic signal-to-noise ratios improved dramatically during the collision's enhanced brightness, enabling detection of species normally too faint to observe. Rare molecular transitions and isotopic variants appeared clearly in spectra that previously showed only the strongest features. This temporary window of enhanced spectroscopic capability provided chemical composition measurements unattainable during normal activity. Spectroscopists prioritized measurements requiring high signal-to-noise, conducting targeted observations of specific transitions while conditions permitted. Adaptive optics systems struggled to maintain lock on the comet's diffuse, extended structure. These systems require bright reference sources to measure atmospheric distortion, but comets lack the point-like nuclei that work best. When the collision's plume temporarily created a brighter, more compact region, adaptive optics performance improved noticeably, delivering sharper images. This experience suggests that future instruments should incorporate algorithms optimized for extended sources to maximize image quality for cometary observations. Coronagraphic techniques attempted to suppress the bright coma and reveal faint features near the nucleus. Coronagraphs, normally used for observing solar corona or exoplanets near bright stars, block central light while allowing peripheral regions through. Applied to the comet, coronagraphy revealed faint jet structures otherwise invisible in the glare. However, achieving good coronographic rejection required precise centering and stability, challenging to maintain for moving targets. Successfully coronographic observations required careful planning and real-time adjustments by skilled operators. Spacecraft instrument responses to unexpected conditions tested autonomous operations capabilities. Some instruments operated under automated rules that selected observing modes based on target characteristics. When the collision suddenly changed those characteristics, automated systems sometimes made suboptimal mode choices. Ground controllers intervened when possible, but light travel delays meant spacecraft sometimes operated for hours under non-ideal configurations before corrections arrived. The experience informed design of future autonomous systems with more robust decision algorithms anticipating wider ranges of possible conditions. Calibration stability under intensive use became concerns as instruments operated nearly continuously rather than with typical intermittent schedules. Photometric calibration requires regular observations of standard stars to track instrument sensitivity changes. Intensive comet monitoring left less time for calibration observations, introducing uncertainties in brightness measurements. Post-processing calibration relied on overlap between different instruments and comparison with previous epochs to detect and correct sensitivity drifts, though uncertainties remained larger than ideal. Data transmission bottlenecks limited how much information spacecraft could return. Spacecraft memory buffers filled with high-resolution images and particle measurements, forcing prioritization decisions about which data to transmit first. Mission operations teams balanced scientific desires for comprehensive data against realistic downlink capabilities, sometimes choosing to transmit lower-resolution versions of more images rather than high-resolution versions of fewer images. These compromises satisfied more researchers but left some questions unanswerable due to insufficient data quality. Post-event analysis identified instrument modifications that would improve performance for future transient events. Recommendations included expanded dynamic range for photometric detectors, faster spectroscopic readout modes, improved adaptive optics algorithms for extended sources, and enhanced autonomous control logic for spacecraft instruments. Implementing these improvements requires investment, but the collision's scientific return demonstrated that preparedness for unexpected events yields high scientific dividends, justifying the costs. Scientific legacy and future outlook. The collision's scientific legacy extends beyond immediate results to reshaping how astronomers approach interstellar visitor studies and transient event monitoring. The experience demonstrated that coordination across multiple observing platforms and research communities produces comprehensive understanding impossible from isolated efforts. This lesson informs planning for future campaigns targeting other interstellar objects or rare cometary phenomena, with organizational structures and communication protocols established during the 3I Atlas campaign serving as templates. Detection capabilities for future collisions will improve as survey facilities reach full operation. The Vera Rubin Observatory's legacy survey of space and time will image the entire visible sky every few nights with sensitivity exceeding current surveys. This capability ensures earlier discovery of interstellar visitors and continuous monitoring throughout their solar system passages, maximizing probability of detecting collision events and other transient phenomena. Automated transient detection pipelines will flag brightness anomalies potentially indicating collisions, triggering rapid response observations by other facilities. Theoretical frameworks for understanding cometary collisions and their consequences matured through confrontation with real data. Pre-collision models made predictions that observations validated or refuted, forcing refinements that improved predictive capability. The next collision detected will benefit from these improved models, enabling more confident interpretation and perhaps even predictive capability about what to expect. This progressive model improvement through successive observations exemplifies how science advances through iterative confrontation between theory and observation. Mission concepts for rendezvous with future interstellar visitors gained momentum from the 3I Atlas experience. Seeing an impact event from hundreds of millions of kilometers emphasized the value of proximity observations. A spacecraft rendezvousing with an interstellar object could deploy impactors deliberately, conducting controlled collision experiments to probe internal structure and composition. Mission planners are now developing concepts for rapid response spacecraft that could launch within months of interstellar object discovery and reach the target before it departs the inner solar system. Educational impacts resonate as the collision story reaches classrooms worldwide. The event provides case studies in multiple disciplines, including astronomy, physics, planetary science, and even statistics and data analysis. Textbooks and curricula incorporate the collision as examples of scientific method in action, showing how unexpected observations drive hypothesis formation, testing, and revision. Students learning from this episode gain appreciation for how real science unfolds messily and iteratively, rather than following idealized, linear progressions from question to answer. Public engagement metrics show sustained interest in interstellar visitors following each new discovery and dramatic event. The collision garnered media coverage and public attention comparable to major space mission milestones, demonstrating astronomy's continued capacity to capture imagination. This engagement has practical benefits for science funding and support, as engaged publics more readily approve investments in research infrastructure. The astronomical community recognizes the importance of communicating results accessibly and promptly to maintain this positive feedback loop between public interest and scientific capability. Philosophical implications about our place in the cosmos emerge from contemplating interstellar visitors and their interactions with our solar system. Each such object represents a messenger from beyond, carrying information about other stellar systems and perhaps provoking reflection about whether life beyond Earth might similarly traverse interstellar space. While the 3I Atlas collision provided no evidence of extraterrestrial intelligence, it reminded humanity that the cosmos contains wonders yet to be discovered, and that maintaining open minds toward unexpected possibilities enriches scientific exploration. The collision marks a milestone in humanity's expanding awareness of the dynamic, interconnected nature of the galaxy. Interstellar space is not an empty void, but rather a vast ocean through which objects drift, occasionally entering stellar systems and interacting with native populations. Understanding these interactions contributes to comprehending galactic ecology, the statistical ensemble of processes by which matter cycles between stellar and interstellar environments. Each data point adds to this emerging picture, and the 3I Atlas collision provided rare empirical evidence constraining theoretical models of galactic-scale matter exchange. Future Outlook anticipates continuing discoveries as survey capabilities expand and more interstellar visitors are detected. Statistical predictions suggest that facilities like Rubin Observatory should detect multiple interstellar objects annually once fully operational. Some fraction will likely experience observable collision events during their solar system passages, building a sample that enables statistical studies currently impossible. Within decades, dozens of interstellar visitor detections could transform the field from novelty to routine, with collision events becoming expected complications rather than shocking surprises. The story of 3I, Atlas, and its collision continues to unfold as researchers analyze data and prepare publications presenting comprehensive findings. Years may pass before all implications are fully understood and integrated into broader theoretical frameworks. Meanwhile, the comet continues its outbound journey, gradually fading from view but leaving behind a wealth of data and a legacy of lessons learned. When the next interstellar visitor arrives and experiences its own collision, astronomers will be ready, equipped with knowledge gained from this extraordinary event to extract maximum scientific value from whatever surprises the universe chooses to deliver.